A short video for ME401 to explain the MATLAB code that I've shared with you. All right, so I put numbers in for the 4-bar that was generated when we did the synthesis of Norton problem 531. So we got a 4-bar, and I've added a driving dyad to it. So let me look back over here under. All right, so here is the driving dyad, and you're well familiar with creating these. Well, I got the lengths of these and the initial angles. I was very careful with the initial angles. Before, many of the MATLAB codes that we've been doing have been using just a ground that is horizontal. Here instead, I modified. Started out by creating this 4-bar right here, this driving dyad 4-bar in the MATLAB code. I'll show you. And you can see that the ground now, this is going to be theta, I call it theta 1. All right, so, and this length is D. All right. One of the things to note is that the crank and the coupler are in line with each other in the initial position. Okay, so anyway, I got the dimensions. Here you go. This is the ground. This dimension right here, this is the crank length, that 37.2 millimeters. And right here, this right here, this 162.8, that is the coupler length, right? And then lastly, I chose when making this driving dyad to make it a 100 diameter. So that's a 50 millimeter diameter crank right there, rocker, sorry. And I also just checked all these different angles. So you might have to do something along those lines to be able to use this MATLAB code. Make sure you get all your dimensions. Be very careful with the reference angles. I decided to use it for my theta 1, a negative 31.5. You can see because it's going clockwise from here. All right. So the same thing true, by the way, needs to be done for the for your main 4-bar, the rocker. You need to get what the ground angle is for right here, and of course all the lengths. And then, okay, also another thing to be aware of, we use this little point, this reference point P1 right here. So when I'm done with this, I'm going to get this length right there, and also this angle, 31.93. So let's go to the MATLAB code and check it out. I wish I could make this larger. We'll just have to deal with it. All right, so here are the input parameters. You can see this A, B, C, and D that we're used to. And here's my theta 1 where I've made a negative 31.5 and of course turned it into radians. Here's the rocker, which is like the main 4-bar. And I decided to continue with dimensions 1, E, F, G, and H, right? So these are the 4-bar resulting. And then I decided to make theta 5 in the same trend where they made the ground is theta 1 in this one. I made theta 5. Here's what the ground is, angle is for the rocker. And then, well, we know that theta 7, okay, so theta 6 is going to be identical in this. Let's see right there, because theta 4 is based on the rocker of this, but that's going to be the input of the rocker. So theta 6 is equal to theta 4, which makes sense. Initial position is 0, and then I also put in an initial position by way of the synthesis gave me an output and told me what this other rocker is going to be, like the second rocker. This rocker right here, its initial angle from horizontal, I don't think it's being shown right here. No, it's not shown on here. But if you were to get it, you would see that to look for the thing, it's like 120.6 degrees. This is, and then of course here's P and gamma. Those are for this angle right here, right? So here's the length P, and then gamma is just the length that's in between this, right? The 31.9. I know this is a really exciting video. Okay, so here is okay, so I also measured the initial position of the crank. So I called TH2I. And then I made a string of TH2, right? So this is going to be actually the length of the thing. And I made increments of degrees, 1 degree each. So it's 2 pi divided by 360 is the, so I'm starting from TH2I, and then I'm going plus 4 times pi. All right, so this one just goes for 2 rotations. And then here's my input RPM. I want 20 RPM. Then I made a string of time, but I started at 0, right? So you'll see I subtracted out there because I divide this string by my omega, and then I get a string of times, but I want to start at 0. All right, so now the calculations start here, and they're really not any different from other 4 bars that we've done. This is the Newton-Raphson, where I have these estimates for theta 3 and theta 4. Here's something important to note. This is the initial position. You could put this as as a hard input. I went ahead and made it law of sines calculation. Guess it doesn't matter, but I decided to go ahead and put this in as part of it, right? It's good to have a good initial estimate for the angle, but you could put numbers in here, I think, because it's going to go ahead and use those in the Newton-Raphson to do the position analysis, right? And then once we're done, we have, and this is for an entire string, remember, where I'm going to go for, I say 4, and then this is the length, right? I actually start at 0.2 because 0.1 has already been kind of established, and run it through the entire length, right? So right here is this the initialization of the thing, and then this is actually the Newton-Raphson right in there, and it just keeps doing a bunch of Newton-Raphsons until it's done, and then I throw away the first line. Now I start to do the whole thing over again, but I'm using theta 7 and theta 8 are the angles for the rocker. And here, I already had the initialization angles up above, so we're going to use those. And then everything's the same. A Newton-Raphson, multi-dimensional Newton-Raphson. And we come out to the end. And then I have, here's I want to see what the shape of that pointer is. So that's what my CCX, I don't know why I chose CC. I must have some reason at some point. But yeah, so this gives a kind of an arc, kind of like check and see what that looks like. It's a sanity check, and then I can get the velocity, and then I can get the acceleration by using the diff commands to take the differential. All right, there. Here we go. Hit go right there. Here's the acceleration and the velocity, and then here's what that arc look like right here. If you want, you can also it's a good idea, uncomment these, run it again. Let me get rid of these. I don't have too many of these figures because I didn't use like the figure labeling thing, which would have stopped it from making new figures every time. But this right here will make a file, an accessible Excel file. Oh, it got mad about something. I think, I don't remember. Let's see. Do I need to fix this? Let's see. This happens quite often. It's unable to. Oh, you know why? It's because I have it open. Do that all the time. All right. So let me run it again. Yep. It was unable to write to it. There you go. If you open up that Excel file, if I can find it again, it's under my MATLAB and examples. I don't label things very well. There you go. Here's that Excel file. what I did is I pasted this into another file right here. So that's just, that's the same information here. And let's see, I've graphed it right here. And then I've run the same thing in Mat and SolidWorks. So here you go. So you can see right there. That's the tip that I'm getting the velocities for. And I've plotted out the X and Y. Let's take a look and show plot. Boom. And here are the X and Y's. And if you want to, you can export them by right-clicking and export to spreadsheet. And a spreadsheet will pop up eventually. There he is right there. So they've plotted this thing out, and you could go ahead and grab this time right here and plot them together. And you can take my word for it. When you do, you'll see that there's on the right here, that's SolidWorks, but you can see that they're right on top of each other right here. Here is the MATLAB X direction, and then here is the SolidWorks X direction, and you can see you can't really even tell there's any difference in between these when they're overlaid. And that's the same thing with the Y, the SolidWorks. Let's see, here's the MATLAB Y right there in the orange, and here is the MATLAB SolidWorks orange. So we got the kinematic. So I am pretty confident this MATLAB code is doing an accurate driving dyad and rocker for your project. So try it out for yourself. Let's see if you can get yours to match up.